Good morning, students. Good morning. So till now, we have covered sequence components of phasors, unbalanced phasors, and sequence networks of various elements of power system. So now we are ready to analyze unsymmetrical faults. As we have discussed that unsymmetrical faults are not so simple as the phasors are unbalanced in nature. So that's why we learn these sequence networks and sequence components of unbalanced phasors. So now we are ready to discuss the unbalanced faults. So first analysis will be for LG fault, single line to ground fault. So unsymmetrical faults may be either SLG, single line to ground, or line to line, or double line to ground. So we will discuss one by one. So today we will discuss SLG fault. Single line to ground fault, line to ground fault. So also known as SLG fault or simply LG faults. So in all unsymmetrical fault calculation, similar to that of symmetrical fault calculation, we will assume that our system is unloaded at the time of fault. When fault occurs, so before that system was unloaded, it means load currents are zero. So the same assumption was there during symmetrical fault calculation. The same assumption will be here also in unsymmetrical fault calculation, right? So let us draw a three-phase network. So let us say this is a three-phase network. This is neutral, and this neutral is grounded through, say, this Zn impedance. R phase, here Y, let us make here B. So the line currents will be, let us say, IR, IY, and IB. This EMF is ER in R phase, EY in Y phase, EB in B phase. The impedances are Z. So we have assumed that our system is unloaded, so no load current will flow. So terminal voltage, suppose in R phase, VR will be same as this ER. If you have assumed that this IR is 0, IY is 0, IB is 0, still fault has not occurred. So system is unloaded means all the currents, the three currents in the three phases will be 0. So once current is 0, so no drop here. So whatever this ER is there, EMF, the same will be here VR. VR is voltage drop between R phase and ground, right? Neutral is grounded. Okay. Now suppose fault has occurred. LG fault means single line to ground fault. So as we are taking R phase as reference, you can take any phase. So again take R as reference and assume that fault has occurred here. LG, this is ground, this is line, is not it? So this fault will be LG. So this time, as you have EMF here, right? So current will flow. Say this current is fault current IF. So this time this IR will not be equal to 0, this will be equal to IF. Whatever current is there in this phase, that will be fault current. And fault current is having its path through ground, neutral, so it will flow. We will see in detail. So now IR is non-zero when fault has occurred, is not it? So IR, IY and IB, these three phases are no longer balanced. Now these phases are not balanced. As you can observe, IR is IF, right? So it means all the three may have its three components: zero sequence component, positive sequence component and negative sequence component. So earlier, before the occurrence of fault, the currents in these two phases were zero. So this time also these will be zero. Only single line to ground fault has occurred, right? So you may write the three components of this now fault current, that is IR. What it will be, as you have taken R as reference, so write here IR0, IY0 plus I or not directly IR1, IR2. These are the three components of this phasor IR, is not it? If still you are having any doubt anywhere, you may ask. I am rubbing this. Okay. So for this case, when a single line to ground fault has occurred in one phase of this three-phase system, you may write what will be VR now, voltage drop across this. What is drop between these two? No drop, man. This is grounded. It means VR will be 0 at this point of time when fault has occurred in this phase. Are you having any doubt? Okay, so right here VR is 0. VR is equal to 0. What is other conditions? These two will be 0 as it is. As we have assumed our system is unloaded before the occurrence of fault, so these two current will not get changed even after the fault. Before unloaded, so 0. After fault, only fault is in this phase, so again 0, no change here, is not it? So these are, and one more, what will be the value of IF? Fault current, whatever the value of this IR is coming out to be. So IR is having three components: IR0, IR1, IR2. So you may evaluate, you know how to get sequence component of currents knowing phase current. So tell me the values of this matrix elements. Okay, 1 1 1, 1 alpha alpha square, 1 alpha square alpha, and here values will be, this is current, right? So for current this will be IR 0. Oh, you are writing components, so IR phasor in R phase, IY, IB. So for this case IY is 0, IB is 0, is not it? So it means these two currents are 0. And what about IR? IR is IF, so you may write this is nothing but IF. So you may easily write the three components of current in R phase, that is IR0 will be equal to, IR0 will be equal to 1 1 1, these two are 0, so that is nothing but IR upon 3, right? What it will be? Root 3, why root 3? 3. Okay, write first IR upon 3. Similarly, IR1, this will also be equal to IR upon 3, as these two phases are 0. IR2 will also be equal to same IR upon. So you may write, this implies, or right here, this implies IR0 is equal to IR1 is equal to IR2 is equal to, these three are 0, is equal to IR by 3. IR upon 3 is equal to IF upon 3. So from here you may write, this implies IF will be equal to 3 times of IR0. Is not it? So this fault current is 3 times of IR0, and that is the current through this neutral. What is IN? Earlier we have seen that this current is 3 times of IR0. So we have one path for fault current from R to ground, again through this neutral to R, is not it? One loop, we have one loop. So what is the magnitude of that fault current? 3 times of IR0. Okay. Next, we have evaluated the sequence currents: zero sequence current, positive sequence current, and negative sequence current. So let us draw the sequence networks for this. So for positive sequence network, this path will not be included. Similarly, for negative sequence network, this path will not be included. For zero, we will include this, right? So first draw for positive. So this is sequence network for positive. So this is having value of ER, and whatever the impedance will be there, positive sequence impedance, let us represent as Z1. You know what is Z1, Z2, Z0. And current through this will be, what will be the current? IR1. This is positive sequence network, right? So in positive sequence network, impedances will be Z1, EMF will be E1, that is E. Only this network will have EMF, right? Other network will not have EMF. Okay. Similarly, draw negative sequence network. So let us represent this as Z2. We know how to find the values of Z1, Z2 knowing the system impedance. And current through this will be IR2, fine, this phasor. And what about zero sequence impedance? Zero sequence impedance will be Z0, and we have neutral grounded through Zn. So equivalent impedance offered to zero sequence current will be 3 times Zn, right? This is neutral, and this will be, we have discussed this, right? Are you having still any doubt? No doubt. Okay, so current through this will be IR0. Fine. So these are reference buses. Write the corresponding terminal drops. So here we will write this as VR1 will be equal to, apply KVL, ER minus IR1 Z1. Similarly, this drop, right? You are writing this drop. Similarly, write this drop known as VR2 will be equal to 0 minus, so directly write minus IR2 Z2. Similarly, write this VR0 will be equal to 0 minus, again no EMF here, so minus whatever the current is there in this network IR0, you have this, right? Equivalent will be Z0 plus 3 times Zn, no doubt. So we have obtained this relationship. This one relationship is this among the sequence components of current flowing through the R phase in which fault has occurred. Second one is this one. As fault has occurred in R phase, so this VR will be equal to 0. So VR is 0, it means VR is 0, it means the three sequence components of this VR will be 0. Sum of all the three components right here. What will be three components? VR0 plus VR1 plus VR2 will be equal to 0. What are these? VR0, VR1, VR2. Three components of this, three sequence components of this. So if VR is 0, it means sum of all the three components will be 0. Is not it? Are you getting or not? Yes. Okay. So VR0 is this drop, VR2 is this drop, and VR1 is this drop. So from this equation, we can say that algebraic sum of all these three drops is 0. One thing. Second thing, from this equation, the three currents in the three circuits, sequence networks, positive sequence network having current IR1, negative sequence network having IR2, zero sequence network having current IR0. This equation says that all these three currents are equal. It is only possible when the three currents are flowing through series connected network, right? So it means these three networks will be series connected. Now the three networks are series connected. Only this information can be obtained from this equation. There may be some other network connected in series, may or may not. So focus on this relation. This says that algebraic sum of all these three drops is equal to 0. So as per KVL, Kirchhoff's voltage law, this is only possible when these three drops are part of a closed loop. Are you getting or not? So from these two relations, we can say that no any other drop will be there in this loop, and we can connect this like this. And from each network, currents are same, and we have derived this, right? IR0 is same as IR1 is equal to IR2 for these conditions. This condition is for SLG fault, single line to ground fault. Are you having any doubt? Right. So current through this may be written as, this is IR0, this is equal to IR1, this is equal to IR2. This can further be equal to, you have written IF upon 3. So this will be nothing but IF upon 3. Please ask me if still you are having any doubt. No doubt. Okay. So from these relations, just write what is, we are going to write this after this. So just write VR0. So VR0 is nothing but this. So write, what is this? This implies minus IR0. We will write this as Z0 equivalent together. So write Z0 equivalent, where Z0 equivalent is this. Just write this as, we know, we have earlier used this. So this combinedly will be denoted by Z0 equivalent. So we have written this VR1. So this is VR1. What is VR1? ER minus, this is plus sign, right here plus ER minus IR1 Z1 plus this plus, okay. So right here in bracket minus IR2 Z2 will be equal to 0, as algebraic sum of all these three drops is 0. So from here we may write this. This implies IR0 is equal to IR1 is equal to IR2. So put everywhere IR0. So this is IR0, this will be IR0, this will be equal to IR0. So take IR0 common, all negative, this negative, this negative, this negative, ER is positive. So you may write IR0 is equal to ER upon Z1 plus Z2 plus Z0 equivalent. Just check it. Are you getting the same? Okay. From this network also you may directly apply KVL. So what is this? This is EMF. All impedances are in series, and whatever the current flowing through this network is same as series connected. Right. So you want to write that current, IR0 or IR1 or IR2 all are same. So that current may be written as this EMF upon sum of all these three impedances. We are getting the same, is not it? So our objective is to find the fault current. So what will be fault current? IF will be equal to, we have evaluated IF is 3 times IR0 and IR0 is this. So 3 times IR0, this will be equal to 3 times ER upon Z1 plus Z2 plus Z0 equivalent, or you may write Z0 plus 3 times Zn, as this Z0 plus 3 times Zn is nothing but Z0 equivalent. So this is the relation for calculating fault current, right? Suppose fault has happened through fault impedance ZF, as we have discussed in previous lectures. Earlier we have discussed that, okay, this is R phase and fault has occurred like this, is not it? So no fault impedance has been considered. It means whatever the drop is here, we have assumed the same drop, no drop here, as impedance is 0, whatever current is, but impedance is 0, so drop will be 0. Now consider that fault impedance is there, ZF. If fault impedance is given, so consider it. This is IF. Whatever the current through this will be IR. This is the same as IF. This current is IF. So earlier we did not consider fault impedance. If fault impedance is given, it means fault current is getting its path through this ground and ground to neutral through Zn, and we have already concluded in previous lectures that through that path only zero sequence current can flow, is not it? Algebraic sum of all the currents in the 3 phases will be equal to 3 times IR0. So what will be corresponding drop through this? Okay, corresponding drop through this will be IFZF, is not it? And IF is 3 times of IR0. So drop will be equal to 3 times of IR0 Z0. So corresponding reflection in zero sequence network. IR0 is current in which network? Zero sequence network. So corresponding reflection will be addition of an impedance thrice of this, similar to that of Zn. Are you getting or not? So if ZF is given, that is fault impedance is given, so our this will be modified to plus 3 times ZF. If ZF is not given, it means ZF is 0. Even though if neutral is solidly grounded means Zn is 0, it means you will put Zn 0. If neutral is ungrounded means Zn will be infinite, so you will put infinity here, infinite. So something upon infinite plus finite infinite, right? So this will be 0. So second conclusion is, if neutral is not grounded, ungrounded, in that case fault current will be 0. Looking strange? Fault has happened. 3-phase system is there. LG fault has occurred. But neutral is ungrounded, no fault current will be there, that will be 0. Because fault current will not get any path for flow of any current, circuit must be completed. If your neutral is ungrounded, so although R phase is touching ground, but the neutral of the system is ungrounded, means disconnected from the ground, so fault current will be 0. Clear? Okay. So if it has been asked in problem, after the occurrence of LG fault, single line to ground fault, evaluate the phase voltages at fault. Phase voltages will be this VR1. First evaluate VR1, VR2, VR0. Now you know IR1 is equal to IR2 is equal to IR0. So you may evaluate these sequence components of the voltages. So once you know sequence component of voltages VR1, VR2, VR0, so you know the relation how to write the phase voltages VR, Vy, Vb. So how to write this? 1, 1, 1, 1 here alpha square, is not it? 1 alpha, alpha square. Now you are writing reverse of that. Knowing sequence components, you are writing the phase voltages. So this will be, tell me the value. VR0, VR1, VR2. Now you know these phases, sequence components of voltages. So knowing this, because VR0 will be evaluated by this, you know IR0, right? You know IF also, 3 times of IR0, right? So if substituting corresponding values, you may evaluate this. Once these 3 phases are known, sequence components are known, so you may write actual one in the 3 phases. What is VR? Okay. So if you have not considered ZF, fault impedance, in that case VR was 0. So whatever the value of VR will be there, you will evaluate VR0, VR1, VR2. So algebraic sum must be equal to 0, just check it. So VR1, VR2, VR0, just add together, put the values of IR, that is EF upon something, Z1, Z2, Z0 equivalent, whatever we evaluated, right? So you will get 0, just check it at home. Leave a space, right? And just check it at home. Fine? Any question till now? Okay, let us solve one problem quickly. And how to reflect that ZF, fault impedance, in this network? That will be connected somewhere here in zero sequence network. So you may write corresponding reflection will be, okay, just represented by this symbol, 3 ZF, like this, 3 ZN, whatever, whichever representation you like, is not it? You may write KVL. So once you will write KVL, then IR0 will be equal to EMF upon sum of all impedances, Z1, Z2, Z0 plus 3 times Zn plus 3 times ZF. Another way to analyze this ZF is that VR will now be equal to, earlier without ZF, VR was equal to 0 as R phase is touching ground. Now the drop VR will be equal to IF ZF, is not it? IF ZF. You know IF, 3 times IR0, the 3 components of this, right? So 3 sequence components, you know the values, clear? So from there also you can get the same result. Just write down one problem. A 3-phase alternator, just write the values. 3-phase alternator, 3-phase, write 10 MVA, 11 kV, just write it. Alternator is having its 0, positive and negative sequence reactances as let us say 0.05 per unit. Are you writing? A 3-phase 10 MVA 11 kV alternator is having its sequence impedances. Zero sequence impedance as this positive, let us say 0.20 per unit, and X2 0. Let us say 15 per unit respectively. Assuming that the alternator is not loaded, find the ratio of fault currents, find the ratio of fault current for LG fault line to ground, or SLG, you may write SLG, more appropriate. What you wrote? Find the ratio of fault currents for single line to ground fault to 3-phase fault. 3-phase fault. When, take two conditions. When, condition number 1, neutral is solidly grounded. Neutral is solidly grounded. Case second, when neutral is grounded through Zn is equal to 0.1 per unit. So in this problem, the specifications of the alternator is as shown: 3-phase, MVA, line voltage 11 kV, whatever. You have to find out these two ratios of fault currents. What is this? Fault current for single line to ground fault, and this is fault current when all the 3 terminals are short circuited, that is symmetrical fault. We have covered this part also, right? So for this fault currents will be balanced, so we can perform our calculation on per phase basis. You know how to do that, right? So today we have covered this part for single line to ground fault, so you know how to calculate the magnitude of this current also, right? So for these two cases you have formula, and just see it. Okay, so for first case we have the formula for fault current, right? So there Zn will be 0. If ZF has not been mentioned in the formula, it means not given. Once it will be mentioned that ZF fault impedance is this, then we will consider otherwise 0, right? So for this case, find out the value of this. So as calculation in per unit is very easy, and these 3 reactances are in per unit already. So what will be EMF per unit? IF, what will be the value of IF? Okay. So IF will be equal to, for single line to ground fault, we are solving first case, means Zn is equal to 0. So for single line to ground fault, we know IF will be equal to 3 times of E, whatever E is there, that will be 1 per unit, isn't it? Right? Upon X1 plus X2, so J, resistance is not given, so Z is nothing but 0 plus J times this, that is Z1. Z1 will be 0 plus J X1. So this will be J times 0.2 plus Z2, 0 plus this 0.15 plus Z0 equivalent. So Zn is 0, so that will be this plus 3 times of 0, that is this. So this will be J times 0.05. Tell me the values. 1 upon J is minus J, right? J square is minus 1. So for J take common, minus J, and tell me the value. This will be equal to 1 per unit, is not it? In per unit, what it is coming out to be? 7.5. Angle is known, minus 90 degree, minus J means minus 90 degree. Just tell me the magnitude. So 7.5 per unit, is not it? So this is per unit. Okay. What about I3 phase? So for I3 phase, IF3 phase, we have seen that our calculation can be done on per phase basis, and that was very simple. E is nothing but 1 per unit, is not it? Upon X1. if condition is balanced, so negative zero sequence components will be 0, is not it? So right here, what it will be? X1 is J 0.2 for the same machine we are talking about, I3 phase. So how much it is coming out to be? Minus J 5 per unit for case 1. Now come to case 2. So whether case 1 or case 2, Zn does not affect the symmetrical fault currents, we know it, as in symmetrical fault, zero sequence components, negative sequence components are absent. So Zn will affect only to the flow of zero sequence current. So it doesn't affect the various values of this Zn, whether neutral is connected to ground or not for 3-phase fault current. Clear? So for this case also I3 phase will be as it is, only this will be changed. So for second case, I am writing here, for second case, write down IF. So IF this time will be equal to 3 into 1. Did you consider this 3 into 1? Yes. So coming out to be this. So this time 3 into 1 upon this plus this, that is 2, 3, 5, 4, 0.4, is not it? So J 0.4 plus additional 3 into Zn. And what is Zn value? 0.1. So 3 into 0.1, J 0.1. So tell me the value quickly. Minus J 4.28 per unit. Okay. So our aim is to calculate these two ratio of this in these two cases. So for first case, what is this ratio? This is equal to, for first case, what is this? For first case, we are taking this upon this. So minus J get cancelled. So this will be equal to 1.5. 1.5. So value in per unit or actual? It is ratio. It is ratio, no unit, unitless. It means you can observe that this fault is more severe than this fault. Clear? Okay, for second case, we will conclude. First tell me the value for second case. The same value. This is equal to this, and the same is coming out to be equal to how much? So this upon this. How much? 0.86. Okay, whatever. Okay, we can conclude that for first case, this fault is more severe than this, 50% more severe, is not it? But for this case, this fault is less severe than this, as ratio is less than 1. So during symmetrical fault analysis, we discussed that the symmetrical fault is the most severe fault in the system, except this condition. For this condition, when neutral is solidly grounded, when neutral of the system is solidly grounded, in that case this fault will be even more severe than this fault. But the occurrence of such single line to ground fault and 3-phase fault, mainly 3-phase fault occurs on transmission line. So if you are talking about probability, so probability of this fault is more, around 50% of total fault, because we are having wide length of lines and like that, right? And for this fault, for this condition, this particular condition, you may take around 2%, 3% like that. But if someone asks, is symmetrical fault always severe, most severe? You can say symmetrical faults are most severe except certain conditions. When condition is this one, neutral is solidly grounded and single line to ground fault has occurred. In that case, that fault is more severe than this. I will take one or 1.5 minutes. So quickly for that, we will write one expression. Sometimes in exams, it may be asked, find the value of reactance Xn. Say, what is Xn? 0 plus Xn will be, Jxn will be equal to Zn. So what is Zn? Reactance connected between neutral and ground. So find the value of Zn or condition on Zn so that the magnitude of SLG fault is more than magnitude of three-phase fault. So how to write that? So you know the relation for this. What is that? In per unit you may write 3 into 1 upon what is, suppose this is x1 plus x2 plus x0 equivalent, is not it? Will be greater than, what is relation for this? 1 per unit upon x1, is not it? Okay, add in this problem for non-salient machine. So non-salient means x1 will be equal to x2, right? So okay, for non-salient we may write these two as equal. So this will be x1. So for this relation you will write, what you will write? 3 times of x1. This implies 3 times of x1 will be equal to, greater than, write this as x1. So 2x1 plus x0 equivalent, right? This implies x1 must be greater than x0 equivalent is nothing but x0 plus 3 times xn, this xn, is not it? So this implies x1 minus x0 upon 3 must be greater than xn. For this case, this is condition on xn. So in that case, when this condition exists, in it means this is more severe than this. If these two are equal, it means severity are same for these two types of faults. If reverse of that is there, it means this one is more severe than this, right? So based on that, problems may be there in exams. Even in GATE, this has been asked. So we will discuss the same concept while solving GATE questions, right? Okay, thank you for today's lecture. Tomorrow we will cover the next type of fault, line to line fault.